Okay, great. Hello, everyone. Thanks for waking up again early. I hope it wasn't too hard. Good. So yesterday we talked about networks, and we talked about what can you do with nodes of the network. And we talked about this idea of how would you automatically define or identify features of nodes or representations of nodes in the network. What I want to do today in this lecture is to talk about how do you reason about groups of nodes, not about individual nodes, but about groups of nodes. And this idea of reasoning about groups of nodes is called community detection in networks. But the way you can think about it, you can think about it also as like graph partitioning or clustering the nodes of the network. And I'll give you a few examples what I mean by the task, and you will see from examples why this is interesting. Here's a network. Each node is a university football team, so American football, not the real football, and they are connected if two teams play against one another. And if you use a visualization software, this is the network you will see. And you can ask, you know, is there any structure in this network? Is there any organization, or is just this kind of mess? And for example, the methods we will talk about will take this network as an input, and what they will produce is something like this. They will identify these densely connected groups, right? And what turns out these groups correspond to, they correspond to these conferences, how these universities are organized, and teams play more games inside the conference and kind of fewer games across conferences, right? But why this task is hard is because that's the input. This is what you see. But if you are careful and analyze the connections carefully, this is kind of the structure you will extract. To give you another example, very different now. This is every node here is a Facebook user, and there's a connection if two people are friends. And this is a social network of one of my students from Stanford. So we took all his friends and how they are connected with each other. And again, the question becomes, what is the structure of this network? Right? Like, do we see any groups of interestingly connected nodes, right? It seems that there is something down there, you know, maybe there is like a group of densely connected nodes up here and so on. It turns out if you take this to the student and ask them, okay, can you manually classify your friends into social groups? What the student will do is, this is what they come up with. They say, there are four groups of, I have four groups of friends. They are friends from my summer internships, from my high school, and then kind of two groups of friends I do sports with. One is around squash, and the other one is around basketball, right? So here you have these four different groups, and certain people belong to more than one group. So these groups are overlapped, right? And again, kind of, this may now seem nice because we drew it this way, but this is really what the input is. And the question is, given this input, can you discover this type of overlapping structure? Okay, so that's what we'll talk about. And the last example, kind of from the life sciences, you can think about protein interactions, around 20,000 proteins in the human body, how they physically interact with each other. And the question is, can you identify kind of groups of densely connected proteins? And the idea is that these groups will be like functional modules. They will tell you about kind of certain functional units of proteins that work together to control or synthesize different processes and so on. So the idea here would be to go and identify these types of modules that, again, some may overlap and so on and so forth. So the question is, how do we define this problem, and how do we start developing solutions to be able to identify these groups of connected nodes? Okay, so on the input, I'm given a graph. For us, generally, these things can be undirected. I'll also talk later about directed graphs. I'll talk about the ones that can have weights on the edges and also can have signs like pluses and minuses, like you are my friend, you are my enemy type of relationship, right? And what I'd like to do, given this as an input, I would like to figure out what are these clusters or these groups of nodes that are connected in an interesting way, okay? So the idea is that I want to cluster nodes based on the connectivity of the network, and my hope is that these clusters that I will identify, they correspond to something real, right? I need to be able then to go look at these clusters and say, hey, I discovered through social communities, I discovered in an unsupervised way the conferences of sports teams, or I discovered, you know, functional modules in a biological network or then a biologist goes and tests these predictions out, right? But the idea is that kind of, I want to cluster these nodes, and I want these clusters to correspond to something real. And if you look at networks, all networks are kind of organized. You have this underlying network with nodes and edges, but very quickly you start thinking about how are these networks organized at this intermediate mesoscale, at the level of groups of nodes, modules, communities, right? And this organization is very important in a number of different settings, and it allows you to detect missing link, figure out how is the society divided along political factions, identify functional modules, and so on and so forth, right? And there are kind of three aspects to this problem. So the first thing is that the structure of these groups, the way they form, can have many different kind of facets to it. It can be kind of non-overlapping, they can overlap, they can be hierarchically nested. So that's kind of interesting modeling question. Then computationally, this is a hard problem. Kind of many formulations that try to get to this problem are MP hard, and most of them kind of don't scale to networks of a few thousand nodes. And the other thing is, because it's unsupervised, it's very hard to evaluate. So either you have null models and try to see whether you can kind of recover the planted structure you put through the null model in there, or you have some external metadata where you say, are these clusters that I detected purely on the network structure, are they pure with regard to some external information I have about that, right? So if you have a social network and you find a cluster, you say, oh, do these people have something special in common? Maybe they all go to the same school, maybe they all have the same town, maybe they are all of the same race, ethnicity, whatever, right? So that's the idea. So the first thing I wanna just briefly mention is this idea, how do you do this how do you formulate the non-overlapping problem? And there are many methods to do this, but basically, essentially, they all have the same intuition. And the intuition is kind of simple. The idea is you want to find sets of nodes that are densely connected with each other. You want to find these kind of parts of the network where are these kind of lots of connections between the members, and there are, let's say, a few connections across between the members. And this is how you can think of networks in terms of nodes and edges, but you can also think of them in terms of adjacency matrices, right? Where here are all the nodes of the network, and a dark dot means that this particular node I and that particular node J are connected. So if you would order the nodes of the network in a particular way, then this type of structure would correspond to this type of adjacency matrix, right? You have a dense set of nodes, so a group of nodes that has many connections between each other, another group of nodes that has many connections with each other, and then these are the cross-group connections, right? And this is sparse, there's fewer of them, right? Of course, the matrix doesn't come to you like this, right? The hard part in graphs is that you can always renumber the nodes, and the network is the same, but the underlying adjacency matrix will basically be permuted. So all this will just look to you as a big mess. So in some sense, the task is, how do you figure out the correct node ordering where this type of structure kind of pops up? So how do you formalize this? Basically, I'll just give you a basic idea of one of the most common formalization of this process problem. The idea is that you want to find a set S. This is the cluster, and I want to have this function phi of S that tells me how good of a cluster have I found, right? And if I have this function, then hopefully, luckily, later I'll be able to optimize over it. So the way you define this function phi is to define these two notions of cut and volume, right? And the idea is that a set S is a good cluster if it has many edges between the members of the set and few edges that cross outside the set. This is, you can think of this as a cut, right? I'm kind of cutting the set of nodes S away from the rest of the net. Okay? The objective that is the most common is called conductance, and conductance is basically just kind of surface to volume type ratio, right? It says the score, the quality of a cluster S is the number of edges I have to cut divided by the volume of that set S. Okay, so edges cut, it's clear, right? It's an edge that one endpoint is in S and the other one is not in S, and volume is the sum of the edge endpoints in S. So the way you can think about this, it's twice the number of edges inside S plus the number of edges that are pointing outside S. So a good cluster would be that, I cut one edge, and I have a huge number of edges inside. Now the question is, how do you go optimize this type of objective function? And for example, spectral clustering is one way to do this. I won't go in more detail about how to do this, because I'll come back to this non-overlapping case later when I'll talk to you about kind of some interesting work about how do you generalize this to more than just edges. Okay, but that's basically the basic idea. Any questions? Yes. Yes, it's definitely possible to use matrix factorization. I will actually show you later one approach how you can use non-negative matrix factorization. So we'll come to that. That's in some sense, you are factorizing this matrix, and you could even think of spectral clustering as a way to, in some sense, factorize a funny transformation of this matrix. All right, I'll come to that. Good question. There was one more. You had a question? Great, you guys are very pedantic, yes. So here I was sloppy. What you usually do, you say, you want to divide this by the maximum of volume of S, comma, volume of S, not S. Right, so basically you take the biggest part, no, it's the, no, the other way. You take the smallest part of the two, right? So here I'm just saying, because otherwise what would happen if you take the entire thing as your cluster, then yes, this is 0. So that's kind of the corner case. It's obviously a useless case to say the entire network is my cluster. So you don't even want to do. Good. So now I want to talk about this case, right? That's more interesting. Groups overlapping. Okay. Right. So I will be given the network, and I want to extract this type of set of groups that overlap, where a single node can belong to multiple groups. And there are many methods to do this. And I will quickly kind of summarize them and then show you why they maybe are not the best thing to use. There is a lot around this idea of what is called stochastic mixed membership models, where you basically have this like a block model. You say there is a group, there is a probability of people to link inside the group, there's a probability to link across groups, and you have this kind of distribution over which groups you belong to. And then, you know, physicists have come up with a number of kind of very heuristic type of procedures that take the network, do something mysterious, and then if you look at those results, they tend to look quite well. And they are all kind of based on this idea that you want to kind of find cliques in the network or somehow collect nodes that are connected with each other and kind of keep building these methods. And of course, there's also matrix factorization. What is interesting, if you start looking at these methods more carefully, it turns out that they are doing something very funny. And I'll show you what that funny thing is. Okay, so you can start asking, if I go deep into these methods and really try to understand, rather than just kind of look at them as given, and then, you know, they show me 3 examples of nice clusters and I'm all sold. But if I really go inside and try to ask, what are these guys assuming about the structure of the network, then what they are really assuming, not knowingly, is that they are assuming that the more communities, the more clusters 2 nodes have in common, the less likely they are connected. Okay, so it basically says for 2 people, the more social circles they belong to together, the less likely they will be friends. Okay, and maybe that doesn't make too much sense, right? So basically what this is saying is that the way you should think, or the way these methods think about the structure of these overlaps is like this. Or here's another picture, right? It says that these nodes that belong to both clusters where there is overlap, right here, they are less likely to be connected with each other than if they would fully belong to just one cluster, okay? And how would this network picture look like? You can think of these 2 groups overlapping, and these nodes here who are in the overlap, they are less likely to be connected with each other than they are to be connected with the other parts of the network. And the easiest way to see this, for example, for this mixed membership stochastic block models is that you have a probability distribution over belonging to communities. So the best thing for you is to belong to the densest community. And as soon as you start belonging to others, you are kind of taking away edges from here, or probability of belonging to one, to kind of spread it out over all these other communities, so the total number of edges you have will decrease, and you won't be able to link to others who are also kind of spread out across communities. So we were quite surprised when we discovered this, so we started asking, okay, is this true in the data? So what we started doing is we went to people and asked them to label us their social networks with with the groups, and then we started measuring what's the probability of a connection given the number of groups a pair of nodes has in common. And kind of maybe not surprisingly in retrospective, the more groups two people have in common, the more likely they are to be connected. Right? If you go to the same class, if you belong to the same university, if you play soccer together and all this and all that, the more of these common activities you have, the more likely you are to be to be connected in the social network, not less likely. So what this means is that the way to think about this is to think about the way communities overlap is in this type of way, right? Like nodes that are in the overlap that share multiple groups in common, they are more likely to be connected than nodes that only have one group in common. So in terms of structure of adjacency matrix, that's the kind of the way to think about it, right? Is that you have these groups, and when they overlap, they basically there is more stuff here because it's the overlap, or more edges there because it's the overlap of two groups. Yes.
Wait for the microphone.
Or I'll repeat. I'm sorry, I'm bad with that.
Yeah, so it always makes me jump up when you say things which are kind of deterministic. They should be more connected. So what we can more loosely, maybe more correctly say, here are some examples in which the overlapping communities have more connection. Doesn't mean that we cannot come up with natural examples in which in the overlap you have less connection. There's no single truth.
Great, sure, completely buy this. I think we were looking at around 20 different examples, or examples we were able to find, and we couldn't find any example of the previous one. Maybe there exists, yes, maybe we just didn't find it, maybe there's even a different galaxy where it does. Sure.
That's different notion of communities.
It's a different notion of communities. Of course, if you are an empiricist, or if you try to apply these methods to real data, then you can start asking, which method is kind of performing best on a given set of data sets, and which of these methods is able to kind of extract me the best and most interpretable results. Of course, I mean, these things can still exist. There is nothing wrong with them, and you can go try to detect them. That, you know, is a useful exercise in persistence, I guess. Whether that will be useful, or that's a different question, right? But yes, I agree. Thank you for the correction. Good.
I'm wondering, like, do you assume that there is some kind of breakpoint to get kind of like subgroups that overlap? Because otherwise, like, if I have two groups and they somehow, I can try to reorder them in a way that they build like a strong, or I can try to build this kind of subgroup as strong as possible. Or I can go do the other way around and try to like order it in a way that like I don't like that I get a sparse subgroup. Let's put it that. Or is that not possible? Like,
I don't see what you're asking.
Okay, like
really.
if we are looking at the adjacency matrices.
This thing, yeah.
Yeah. So they are probably primarily defined by the very sparse things in the left lower and the upper right corner.
You mean this part?
Yeah.
Yeah. I mean, maybe it's a good philosophical discussion to say actually there are three groups here. There is group number one, group number three. Group number one, number two, number three. Yeah. And then this group is as connected inside as it is connected to the group two. Group two is quite well connected with each other, and then this group three again has the same level of connectivity inside as it has to the group two. So you could think that this overlap is a separate group. I think you can do that, but then again the question is, what is the problem we are solving and what are we trying to achieve, right? So,
okay.
Yeah.
But like, or do you see in your data that you can have the three groups, or is it more or less like kind of additive way that say like, okay, those people which belong to both groups are like especially highly connected? Like
I mean,
would
this says the effect is kind of additive, right? Like we can argue what's the shape of this curve and how this you know what is this thing. But I think the important point is that it goes up. Now is the overlap exact? Like what is the density here compared to the density there, and how does this density increase as function of those densities? That's a good question.
Thank you.
All right, sure. Moving on. So kind of what's the point? The point is that if you have, the way you should think about these groups is that you should think of them as tiles, right? So when these tiles overlap, there is more stuff, the thickness is higher than where those tiles don't overlap, right? So you don't want to think of this as, in some sense, partitioning or cutting things apart. You really think of it as kind of having these tiles and taking them one after another. So now I want to build on this intuition of these groups as tiles, and I want to show some examples of how can you build a model that respects this type of structure. And then I'll just show you kind of one example of the application. Okay? So the way we'll do this is we'll come up with a generative model, and then we'll try to feed that generative model to the data. And the way we will come up with this generative model, it's a very simple intuition. We'll basically think of this as a kind of a union of Erdos-Renyi graphs, if you know. And if you don't, I'll explain. Right? So the idea is that if I have my network, I will model it with with another network, with this type of bipartite network, where at the bottom I will have all the nodes of the network, and on the top I'll have all the groups. Okay? And then every group will have a single parameter, and that parameter will be the probability that two nodes that belong to that group are connected. Right? So the idea is that for all pairs of nodes that belong to the group, I flip a coin, and with probability P sub A, I create a connection between them. And similarly, for all the nodes that belong to group B, for all pairs, I flip the coin, and I put in an edge there with that probability. Of course, the question becomes, what do I do with these guys in the middle? They belong to two communities, right? So what do I do for them? I flip two independent coins, one with P sub A and one with P sub B. So it's kind of natural that these guys will be more likely to be connected because they get two coin flips, not just one. Okay? So this is basically the idea for the model. So the way I parameterize it, V is the vertex set, C is a set of clusters. I need to define the memberships of how vertices belong to the clusters, and then each cluster, each community is characterized with a single parameter that says what's kind of the density of that community, what's the probability of an edge. Okay. So now, if you give me this type of structure, it's very easy for me to create edges for you, right? Basically, I can go and flip these coins. The way you write out the probability of an edge between a pair of nodes, it's simply you say it's a probability that at least one of the coin flips over the communities that you and we have in common comes up heads, right? So it's kind of one out of these events, each one happens with P sub C. So this is none of the coins comes up heads. One minus that is a probability that at least one comes up, right? And now you also see why, as this overlap is getting bigger, the product here is getting longer. This is less than one, so this will be getting a smaller and smaller number. So one minus a smaller number is a bigger number, right? And of course, given all the caveats and everything, I should mention that for this particular model, it is in some sense making it's making this assumption that these groups kind of independently create edges, and that you are then kind of superimposing these groups one over the other. There might be other, and I would just argue that this is kind of the simplest way to get this tiling effect, to get this effect that in the overlap there's more edges. There might be other ways how you could try to build this into the model. What is nice is that this model is so simple that you can actually start proving properties about them. And what I mean by properties, you can prove how the global structure of the network will look like. So for example, you can prove the degree distribution. So the number of connections associated with every node will follow a heavy-tailed distribution, like a power law. Okay? And you can prove other properties as well. Why this is interesting is now that if I have this type of a model, if somebody gives me this, it's very easy for me to generate the network, right? The way I generate the network is for every pair of nodes, I compute the probability of an edge based on how many groups they have in common, and then I flip a coin with that probability, and if it says yes, I put in an edge, otherwise I move to the next pair. Okay? So from this, I can go to something like that. Okay? Now, just to be very precise, what this means, the way this is defined now is that if a pair of nodes has 0 communities in common, then the probability of connection will be 0. So what you can do is you can assume that kind of there is some background probabilities of an edge, you know, there is some small probability epsilon that will add you the edges, and this way, let's say, make the network connect. Okay? But essentially, that's how you can think about it. Why is this interesting? Is because it allows you to model many different types of network structure. Right? So for example, if you want to have non-overlapping communities, then here's the bipartite graph that would allow you to model groups A and B that don't overlap, right? And there might be some edges across if you assume this background probability of a connection being epsilon or something, some small number. Okay? So that's the first idea. The second idea, if I want to model overlaps, I can have nodes that belong to both sides. And if I want to model, for example, hierarchically nested organization, right, where I have this mother group B that A and C both belong to it, then here is how I can organize, how I can represent this, right? I have this B that everyone belongs to, and then subgroups also belongs to C, and subgroup of nodes belongs to A. Okay? So it's kind of very natural to model things this way. So now that we have this type of a model, I kind of want to go the other way. I want to be able to feed this model to the data. Okay? So what's the task? Given this graph, I want to find this model B. Should I touch anything or not touch? Okay. Okay, super. So I want to go from graph to the model. And the way I'd like to do this, I'd like to pose this as a maximum likelihood type of a problem. The way in networks, the way you write out the likelihood is the following way, right? You say, what's the probability of me seeing the graph given the model? And basically what you have to do is you have to go over all the edges of the graph and say, here's the probability of that edge existing as assigned by the model. And then you have to also go kind of over all the negative evidence, all the edges that are not existing in the graph, and say, aha, and here's the, 1 minus the probability that the model assigns to the existence of that edge. Okay? What do you notice is that computing this is expensive because you have to go over all the edges, but also over all the non-edges, over all the edges that don't exist in the network. And real networks are usually very sparse, right? Like, even if you think about in terms of adjacency matrix, the possible number of edges increases quadratically with the number of nodes. But usually degrees, the fraction of connections people have is usually some constant number. So density is very, very low. So you have few edges and many non-edges. So computing this explicitly is many times infeasible. So the way you can start thinking about fitting this is the following way. So rather than think about what we will do is we will kind of relax this model a bit, right? And the way we will relax this model is to assume that memberships, me belonging to a given group, I belong it with a given strength. Okay, so I still have this graph as I had before. Before I had this kind of hard assignments of nodes to groups, but now I will have every edge will have a non-zero weight, and this weight will tell me how much does a given node belong to a given group, right? So this is the node, and that's the group, okay? And I can think of this as the membership strength of node U to the group A. And if the strength is 0, then I'm not a member of that group, okay? So that's how we can do it. Now that I have this, I need to go and kind of define the probability of a connection. And the way I'll go define this is the following way. Here is how I'll model it, right? I'll say the probability of a connection between you and me is 1 minus e raised to the power of minus, and then I have a dot product of the membership vector of U and a membership vector of V. Okay, so what this is basically saying is to say, I have my membership vector, you have yours, let's multiply them together, so let's see what groups we have in common, and then whatever is your strength to that and my strength to that, let's multiply that, and that's kind of the contribution of that group. And then let's add that up over all the groups we have in common, right? So that's the way to think about this expression, okay? Of course, this is highly non-convex because I have this product here, right? These f's, these are in some sense parameters of my model, and I'm multiplying them together. So I will kind of never be able to figure out what is the global optimum of this, but I can try to use some kind of gradient descent type techniques to try to figure this out. So now, how do I figure out f? Okay, so I need to figure out this matrix f that tells me for every node what is the group membership for the node. Okay, and once I have that, then that defines me these probabilities of connection. So here's now the idea. Here is how I write out the log likelihood, as we had it before, right? So the log likelihood of seeing the graph given the node community memberships f is the following. Again, I go over all the edges of the network, and here's the log probability of seeing the edge, right? So this thing is just the blue thing above, and here is a sum over all the non-edges of the log of 1 minus 1 minus x. So all that is left, right, is the factors, the memberships of U and the memberships of V, the dot product together. Okay. So what I'm trying to do now is find f that maximizes the log likelihood. Okay. Where does the data come in play? Data determines tells me what is the set E, what are the edges that exist in the graph, and what are the edges that don't exist in the graph. Okay, so I'm trying to make the probabilities of edges that I see in the network to be high, and I want the probabilities of edges that don't appear in the network to be low, right? I want these dot products to be low, and I want these dot products to be high. Okay, so the way you can think about this, you can think of this as some way of non-negative matrix factorization, right? The reason you can think of this is that you have your adjacency matrix of the graph, and you want to figure out this matrix F when you kind of multiply it with itself using this type of expression or this type of loss function. It will kind of reconstruct the underlying edges of the matrix, the underlying matrix as well as possible. So the way we will do this is we will do this kind of iterative method where we will go over nodes one by one, and for every node we will go and try to update its memberships, and while keeping the memberships of all other nodes constant, and we will kind of iterate this over this many times until we kind of get stuck in the local mean. Okay, so I want to say that the strength of the membership of node U due to group C, I'll try to update this while fixing the memberships of all other nodes. And what I want to now show you is how can you update this, how do you work this out, and how do you update it quickly. So if I take the derivative or the gradient of the log likelihood with respect to the memberships of a single node, this is what I will get, right? So what I get is it's a sum over all the neighbors of node U, because I'm trying to figure out what is the membership, what are the strengths of memberships of node U to communities. I need to go over all the neighbors of U. Here is now the community's membership strength of V, and here are now these dot products of U with every member V. And then what I also have to do is go over all other nodes of the network who are not members of U, neighbors of U, and sum up their membership strengths, right? What's the problem? The problem is that computing this thing is very expensive, because I have to go through the entire network, through all the nodes of the network to get this, right? If the degrees in generally are low, so the set n will be small. So computing this guy is very fast, but computing that guy is very slow. So what I can do is the following. If I would just want to iterate this and do some kind of stochastic gradient descent or gradient descent, this would be prohibitively slow. So what I can do is I can make the following observation. I can make an observation that this particular summation over all the non-neighbors of U can be broken down the following way. It's a summation over all the nodes minus whatever is the factor for node U minus whatever is the sum of the factors of the neighbors, right? Kind of by definition. Sum over all the non-neighbors of U is the same as sum over everyone minus U minus the neighbors of U. Kind of very simple, right? But why is this clever? It's clever because I can cache this particular sum. Kind of every so often I update it, but then I keep it, I save it, and then whenever I need to compute this term, all I have to do is subtract this and subtract the sum over the neighbors, right? And that's it. So this way I can do this much faster, and I don't need to traverse every network, the entire network, whenever I update memberships of a node. Okay? So with this I can really run this, and I can run it very fast. So let me show you how well this works. I showed you this example before of this Facebook network where we asked the students to explicitly label every neighbor to what group they belong to. Here are the examples how some methods would look. If you run this, what is called link clustering, developed by physicists, these are the groups it would identify. It would say that there are 3, and here is what they look like. What stochastic block model does, it will identify this. It will say, oh, there is this one giant kind of group that is the background, and here are now these other groups that are kind of imposed on top of it. And why is it doing this? Is because these two are a bit less well connected than these other two. So it's in some sense just trying to model density. It says, let's paint this canvas as a background, and then, oh, here is a bit more density, so let's throw one more thing here. Oh, and there's more density here, so let's put even more here, right? And here's another method that kind of also doesn't do the right thing. If you look at what the method I just explained to you does, it will detect this thing with 94% accuracy. And this is exactly the same picture as I was showing before. What I didn't explain before is that the dot, whether the circle is fully colored or whether it's not, is kind of gray, is the following. So fully colored means that the algorithm assigned the node to the correct group, the same group as assigned by the human, and these guys are the mistakes, right? So the human put this guy into some other group, not in the Stanford squash group, right? And you see that, there are a few mistakes, and overall, I think the total accuracy of the method is 94%. And you see that overlaps are beautifully well extracted. There is one mistake here, but at least inside this core of the network, we identify these things quite well. Okay, this is what I wanted to say here. Any questions? Yes? Great. How do I How do I determine the number of clusters? Because it's a generative model, what you can always do is you can always do kind of cross-validation over trying to predict the edges of the network, right? Because this model, if you think about it, right? If I go to the picture, kind of what it tries to do, it tries to predict the edges of the network. So you can think of this as a prediction task. What the model is trying to do is tries to predict the edges of the network, and it says, I will predict edges of the network by kind of assuming nodes belong to groups, right? So the group memberships are just kind of the side effect of you trying to predict the edges. So you can ask, if through some cross-validation procedure, what is the best number of groups that predicts the edges the best? This is the way we determine automatic number of clusters. Okay, I want to quickly show an extension, if you think about these applications to discovering social circles, which is these groups of nodes in the networks. What I ignored so far is that nodes have attributes, right? So far I said, let's just take this undirected network structure and take that in as an input. What I can do in let's say social networks is that nodes also have attributes. So what I can do is I can think of the problem the following way. I can say, let's have every node, let's assume it's associated with a binary vector, and this binary vector tells me something about the node. So, you know, maybe the first column is, did you go to Stanford to school or not, right? And maybe this feature is, were you born in 1984? Yes, no. Right? If I have these binary features with the node, then for every edge, I can now ask, you know, which of the features that are set to 1 do these two nodes have in common, right? So this particular pair of nodes, they have in common this particular feature that says they went to Stanford together, and this other one that they were born in the same year. But whatever is this last feature, only the left node has it, but the right node does not. Okay? So now what I can try to do is to say, how would I take this type of information and bring it into this idea of group detection or social circle detection. And the idea here, how you can use this information is the following. The idea is that every of these groups, right, is created because these people have something in common. Okay, so the idea is that these circles will arise for a specific reason, because there is a specific feature or a specific set of features in common between those people. So the way you can encode this is the following, is to say that probability between x and y, of an edge between x and y, and I'm really sorry because I was using u and v and I was using I and j, and now I'm using x and y, and hopefully now I run out of letters, so I won't surprise you with another way. But right, the probability between, you know, use your two favorite letters, is the way you can think about it is the following. What we will have is this phi xy is this feature vector that I had that I showed before on an edge, right? So it's kind of what does the pair of nodes have in common, and then for every of these social circles, I will have like a prototype vector. And what this specific circle specific weight vector will tell me is for that particular node to belong, if they belong to this particular circle, what is the importance of having that feature for creation of the edge? So the way you could think about it, if here is my weight vector, then you could think that circle specific, this is my feature vector, and then the way you can think about it is that this circle specific vector would tell you what is the for the pair of nodes that belongs to this circle, how can I explain the edge, and which features have to be turned on for this edge to be well explained. Okay? And I can again kind of do the same thing as I was doing before. I have now probability of an edge. I can write out the log likelihood, and I can optimize two things. I need to decide what circles do nodes belong to, and then for every circle, I want to find this weight vector that tells me what are the features that are important for this pair of nodes to have in common, right? So before, all I was doing was to say, what's the strength of node U to belong to a circle? Now I'm saying, for every circle, let's also have this weight vector that tells me what features are important to have in common for people, for the members of that circle. And if you run this, it works amazingly well. So this is again a social network of one of my other students. And what I'm showing you here is the same network 3 times. And these are the 3 social circles we identify. Blue is based on, again, what the student labeled the network before we even run the algorithm. Blue are the kind of correct predictions, and red are the mistakes. And you kind of see it's quite blue. That's all I would say here. What is interesting is if you go look now into this weight vector, what are feature importances? Here I'm plotting the features, and the bar height is the weight. And what is cool, for example, is that it turns out that, you know, whoever belongs to this group, what they have in common is they have this American in common, right? So their nationality is American. That's one thing, right? For example, this group here that's nested in these American groups, what these groups, the high weights here are living in Stanford or San Francisco, and you have to have or people here tend to have PhDs, right? And then this last group here, that is here. What do people have in common here? They are Germans and they went to school in 1997. Okay, this is a group. This is a social network of one of my students. His name is Bob. He's German, and he had a number of American friends in San Francisco. He obviously he went to Stanford. He was living in San Francisco, and he went to school in 1997. And yeah, he's German, right? So it kind of nicely explains the structure of his network, and it also nicely kind of explains the structure, right? There is this Americans cluster. This Americans cluster has kind of a subcluster of people who live in SF, and then there is this other thing that's kind of two parts, right? These are these Germans. Some of them are also living in United States, and there is this other kind of non-US part of his German friends. Yes. We scraped, which features did we put in? We scraped the profile of people and created a feature vector out of that. So this is Facebook network, so it's Facebook profile features. Of course, we didn't now have people who went, because the feature space is smaller than you think, because people enter their high school and they say when they went to high school. So Bob doesn't have friends who went to high school in 1700, right? So that's why the cardinality, there was this binary feature for go to high school for every possible year. And there is a couple of possible years in his social network, right? In the entire Facebook graph, there is many more different features. But here, because the number of people is small, you only see kind of a subset of the universe of all features. Okay, good. So anything else? Yeah.
Side information from members of the net saying that, you know, I know that there is this group and exists, and how you can incorporate that explanation.
That's a great question. So I guess the question is kind of how could you supervise this? Actually, I haven't seen any good solutions. I think it's a super interesting problem. How would you kind of supervise clustering in some sense? Whatever that precisely means. It's not even clear to me what exactly. I haven't seen people do that. Great. There was a paper it tips last year. Can you say more?
Pairs of nodes, whether they should, you know.
I see. Great. I wasn't aware of that, but that's great. So NIPS. Yeah. Okay. Great. Thousands of papers. There's always something to do. So what I want to do next, the last thing I want to talk about is this idea, not that you only want to cluster based on edges, but you want to cluster based on structures that are bigger than just individual edges. So let me explain this thing, it's quite cool. Okay, so the idea is the following. The idea is that if you look at networks are not just kind of a set of nodes and a set of edges. Networks are, one way you can think about them is that they are composed of this type of small substructures, and you can think of a network as a set of small subgraphs, right? And here I'm showing you all possible subgraphs on 3 nodes. And in this case, these subgraphs are directed, right? So there is 13 ways how you can take 3 nodes and create a connected subgraph out of them. And, you know, they go out of, you know, there's a cycle, these types of structures, so on and so forth. And it turns out that these types of structures are very important for the structure and the function of these complex networks. And the way to think about this is that before I kind of go on, these types of structures, depending on what community you are at, you can call it a motif, you can call it a graphlet. But at the end, it's the same thing. The idea is that you want to kind of look at this induced subgraphs embedded in the bigger network. And why is it useful to think about these types of things this way is, here's an example. If you think of, let's say I have a network and let's say I have 3 clusters. Then it turns out that in social networks, what you see in social networks is lots of triangles, right? If you have 2 people that have a friend in common, then the probability of them being friends with themselves is very high. This is called triadic closure, right? It's like if the 2 of us have a friend in common, then usually what happens, that friend will introduce us or will bump together at a party and there will be a link created. And this is the process that social scientists call triadic closure. So real world networks have lots of triangles, many more than what you would expect if the connections would be random based, and you would say, right, because the more edges you have, the more triangles you'll have to have by chance as the network is getting denser. But real networks have like orders of magnitude more triangles than what you'd expect just based on the size and the number of edges. Okay, so triangles are important. And why am I trying to illustrate here? What I'm trying to illustrate is if you can say what is the strength of the connection between these 2 clusters versus those 2 clusters, right? In some sense, you could say, oh, there are 3 edges across here, and there are 3 edges across there. But if assuming this is a social network, what you notice here that these 3 edges here, they are forming triangles, right? So these connections are in some sense much stronger than here, where it's just these kind of isolated connections crossing between the 2 clusters. So basically, it's kind of saying that triangle motifs are presenting stronger social ties. So the strength of these things is much stronger than the strand there. So it means that basically not all edges are equal, right? Depending on what kind of structure an edge belongs to, the strength of the edge might be different, or the importance of that edge might be different. To give you another example, here I'm talking about I'm talking about transcription networks, where what in these types of networks is very important. These are now directed networks. Is this idea of feedforward loops, right? Where 2 nodes can be connected directly, and then there is this kind of path through a common friend that goes around, and this is called the feedforward loop because you can go here or you can take the longer path. And it turns out that these types of motifs are very important because they tell you kind of how information is being processed or how signals are being processed in these networks, where you can go directly or there's kind of a common intermediate, right? And again, the question starts to become, how could I start to understand the organization of these networks at the level of these types of motifs, right? And for example, if you are interested in feedforward loops, then you would say, oh, here's this set of nodes that has lots of feedforward loops between them. Okay, so what is the idea? The idea is, can I be given a subgraph and can I find a cluster of that subgraph? Okay, so let me make this more precise. So the idea will be that I want to find clusters, modules, not of edges, but of motifs. Okay, so on the input, I'll be given a graph, let's say a directed graph, and I'll be given a motif of interest, right? The human comes to me and says, give me clusters of this type of structure, right? So now if I ask, where does this type of structure appear? If you can see here, right, this is a bidirectional edge. Here are the bidirectional edges, and these are unidirectional edges, right? So they are here. So in this particular cluster, if you look at it, this particular motif appears here, right? So what I'd like to do is, I'd like to define this as a cluster, okay? And what is interesting to observe, the interesting thing is to observe that everything I was telling you so far, I was saying clusters have lots of edges between them and so on and so forth, right? This would be, using our previous method, this would be an amazingly terrible cluster, right? I have to cut all these connections, I have to cut all those, and then, I get, I don't know, 6 connections inside or whatever, right? It's a terrible cluster, right? So, but the question is, it's still a useful cluster because I'm like, this is an important substructure to me. Find me a set of nodes or a part of the network where this substructure tends to appear a lot. Okay? So that's essentially the idea. And what you have to notice is that given the substructure, I will discover different types of clusters, right? So if you are interested in this particular type of triangle, this is the cluster I should discover. But if you are interested in, let's say, that particular triangle, now all the edges are bidirectional, these are the clusters I should discover, right? Because here are all these bidirectional triangles in these cliques, right? So these are the clusters I should discover. If this is the structure you are interested in, but if you are interested in that particular structure, then I should discover the orange cluster for you. Okay? So that's essentially the idea, or that's the taking this idea of graph partitioning or module discovery, but not just discover modules of individual edges, but let's discover kind of clusters where a particular substructure, particular motif is kind of overexpressed, or the network is dense in that motif. Okay, that's the idea. So the question is, how do you go do that? Okay, and I'll recap what I already told you. Okay, so what I'll start with is the old idea. The idea I tried to convey in the first few slides of the lecture, where I said, if you want to find clusters, the way to do is to go find sets of nodes that are densely connected, which find sets of nodes where there's many connections between the members of the set. And I showed you this slide already, where I said the way to do this is to define this objective function phi, and I want to kind of quantify this notion of how many edges are inside the set and how many edges are pointing outside the set. And I also showed you this guy, where I said one way to define this is to define the notion of conductance, which is the number of edges cut divided by the volume. Okay, where the way we define volume is the number of edge endpoints in S, is the sum of the degrees, right? And sum of the degrees is really twice the number of edges inside, right? If I go back, right? Sum of the degrees in S, it's twice the number of edges, because every edge has 2 endpoints, so I count this edge point here, and I count it there, plus the number of edges pointing outside. Okay, so essentially it's how many stuff is inside the cluster. Okay, and now I can go and try to find this thing. Okay, so this is now for edges, but we don't want edges. We want these motifs. So the question is, how do I take this thing I just showed and generalize it to network motifs? The way I can do this is kind of, it's very, very natural, right? So I need to define this cut metric. How many edges do I cut? If I don't care about edges, but I care about motifs, then I can define how many motifs did I cut. Okay, so I ask how many motifs are there where, you know, one part of the motif is on one side of the cut and some other part of the motif is on the other side of the cut. I'm asking how many motifs, how many instances of a motif do I cut? Okay, that's the cut metric. Now I need to define the volume. The volume in the edge setting is the number of edge endpoints in S. So I can also define it in terms with respect to the motif M, where I say the number of motif endpoints in S. Right? Again, very natural definition. And then, right now I have the cut, I have the volume. So how do I define conductance? I just kind of do the same thing as before. I say, how many motifs do I cut divided by the volume of that motif? Okay. Let me now give you an example so that we understand how this works. Okay. Here is a network. Here is a motif I'm interested in. And let's say I want to partition this network in half using this particular cut. And let's say this is the cluster S that I'm interested in. So the question is, what's the motif conductance of this cluster S, of this set S? Okay, so how would I go compute it, everything we know so far? So the first thing I need to do is I need to identify all the instances of this motif. Okay, to make it easy for you, here I colored them, right? So, you know, here's an instance of the motif, here's one, and up there are 3. There is one here, and then it's 1, 2, 3, and 1, 2, 5. Okay, so now, okay, what's the number of motifs cut by this particular by this particular cut, right? I'm cutting one motif, right? That's the one instance of the motif that we have to cut. So we know that up here I have 1. Okay, what about the motif volume? We said motif volume is the number of motif endpoints in S. So if I say how many motif endpoints are in here, there is 10, right? There are why 10? Because there are 3 instances of the motif fully included in S, so that's 3 times 3. And then there is this node again, because this is another motif instance, and that's 1 endpoint. So it's 9 plus 1 equals 10. Okay? So the motif conductance for this thing is 1 over 10. Okay, so we found a good cluster. Yes?
So you mentioned that there is a minimum between the two S and S prime. Is it going to be a minimum of the number of motifs, or still the minimum of the number of nodes?
It will no. The when you define conductance, when you divide by the volume, and and you divide by the volume that is on the smaller side, right? So just think of this as this network continues here forever and everything. Okay, so what you divide here should be minimum of the motif volume in S and not in S. Any,
Hi, 2 questions. Why is it a sensible thing to look at motif endpoints? Because, well, here's one endpoint in the cluster, but you effectively you give a bonus for cutting, right? Because why not just the number of motifs?
Great question. I get bonus for cutting, but still, if I cut, I get 1. I don't get 3. If I fully enclose, I get 3 points. If I cut, I only get 1 point.
But why not just the number of motifs in there?
Great.
Or the number of motifs times edges in the motif, something like that.
Because then you cannot prove anything.
Okay.
So with this, you can actually prove stuff.
And the other question is, given that subgraph isomorphism is already NP-hard, how scalable is this?
I will come to that. I can run this on a graph of 1.5 billion edges. I'll come to that. If I don't, remind me when I'll explain the method to the end. I'll explain. I'll explain later, okay? It's a really good question. Good. So now I showed you my objective function. So what's the point now? The point is, okay, given a graph and given a motif M, find me a set of nodes that minimizes this motif conductance, right? Let's go and find the set S that minimizes this thing, right? What is the bad news? The bad news that finding the set with minimal motif conductance is intractable. You can show it's NP-hard. Even finding the set S with minimal, just normal conductance, with minimal edge conductance is hard. So this is hard as well, right? So now, what can you do? How can you make progress on this? And here is kind of the surprising thing. The surprising thing is that you can actually build an approximation algorithm that will probably find near optimal clustering in your net, right? So the method is called motif spectral clustering, and the way it works is the following: you are given a graph and the motif as an input, and what we will do is the following: using this graph G and the motif M, we will create a new weighted graph W. So we will transform G to create a new graph W. And then we will apply this super cool, super old method called spectral clustering on this graph W. And whatever the spectral clustering on W finds, whatever are the clusters it finds, we will output these clusters. There is a very nice theorem that goes with this that says that resulting clusters that we obtain by using this procedure will have near optimal motif conductance. Okay, so in some sense, what we will do is we'll take our graph and the motif, we will somehow transform this graph to obtain a new graph, and then we will run simple edge-based clustering on this transformed graph, and whatever clusters the edge-based clustering will find on this transformed graph, those clusters are near optimal with respect to the original graph and to the motif we chose. Okay. So let me tell you now how this works. Okay, so the idea is I'm given a graph and I'm given a motif, and now I'll take this graph and transform it into a new graph, into my graph W. This W will be weighted, And the way this graph will be created will depend, of course, also on the motif you are given to me. And the way we will set the weights of this graph, we'll say that the weight of an edge ij in this graph is simply the number of times particular edge ij participates in motif f in motif m in graph G. Okay, so here's now my unweighted my graph, and here are now the weights I assign. So, for example, why does this edge have weight 2? It has, if I look at what are the motifs here in this graph, here they are. Right, this edge here participates in 2 instances of the motif of interest, so it has weight 2. Okay, and if you look at, for example, this particular edge here, why does it have weight 1? It has weight 1 because it participates in 1 instance of the motif, right? And this guy here has 3 because it participates in 3 instances. Notice also that there is no edge here because this particular edge 7, 9 participates in 0 instances of my motif. Okay. So now, what I just did, I took my weight, I took my directed graph, I took my motif, I created an undirected graph out of it that has weights. So now that I have this, what is the insight? The insight is that applying edge-based spectral clustering, just a standard method on this weighted graph, will find clusters of low motif conductance with respect to the original graph G. Okay, so that's the main insight, and that's kind of the cool part. So let me now show you what the algorithm is. Okay, the algorithm is take the graph and the motif and create this weighted adjacency matrix, right, where these weights are the number of times a particular edge appears or participates in the motif of interest. Now that I have this weighted adjacency matrix, I apply standard old school spectral clustering. What does that mean is I take my W, here it is, and I create the Laplacian matrix, which basically D is the matrix. It's a diagonal matrix of degrees, and I'm kind of appropriately normalizing W to account for the degree of every node. Once I have this Laplacian matrix, I compute the eigenvector corresponding to the second smallest eigenvalue. This vector Z is called the Fiedler vector. And then I just normalize it again with respect to the degrees of the nodes. So all I did is I took my graph, I created W, I slightly transformed it, and then I computed a particular eigenvector that goes with together with a particular eigenvalue. Okay, so now I have this Fiedler vector F. So the way you can think of this Fiedler vector, it's basically the dimensionality of this vector is the number of nodes in the graph. So you can think of this F as assigning a number to every node in the graph, right? The number of nodes is the dimensionality of this thing, so I can think of every node having assigned a number. So what do I do in the step 3 of the procedure is I run what is called a sweep procedure. The way I run the sweep procedure is the following. I will go and I will order the nodes in terms of their values in the Fiedler vector, right? So I will take the guy with the largest with the largest value assigned by the Fiedler vector to the left, and then the second largest, third largest, and so on and so forth, right? So I just order the nodes according to the values assigned to them in this vector F. Okay. Now that I have nodes ordered, what I do is I create this nested sets of increasing size. So I will say that there is this set S sub R, where it includes R nodes with the largest, right here I sorted them, let's say in increasing order, right? So these are the first R nodes in this ordering, right? And then what I do is I will call this a candidate cluster. So now I can plot as a function of R what is the motif conductance. Okay, so here is a cluster of size 1, this is cluster of size 2, cluster of size 3, 4, 5, and so on. Okay, is it clear what I'm doing? Yes? Okay, great. How about this side? No? Shall I say again? You don't care? Okay, great. I got one node. It will be good enough. Okay, great. So what I'm doing is I sorted the nodes according to the values in this vector, and now I'm taking the first R nodes in this ordering, and I'm asking what's the motif conductance of the first R nodes, right? I'm asking how good of a cluster I get if I take the first R nodes. And here I'm plotting you R and the conductance, right? And wherever this curve drops and reaches the local or global minima, depending on the method I'm using, I proclaim that as a cluster. Okay? So on the previous graph I showed you, here's the global minima of this motif conductance. It reaches it at SR R equal 5, and what are the nodes that are in SR? Here are the first 5 nodes. Okay, so I discovered the cluster I was showing you before. Good. So what is the theorem? The theorem is that in spectral clustering there is this famous inequality called Chigger inequality that gives you guarantee on how well this procedure will find the clusters. As far as I know, this is the only clustering or community detection method that comes with an approximation or with a theoretical performance guarantee. Everything else is kind of non-convex and there's no guarantees. But here you actually find this guarantee, right? And the point is that this is kind of independent of the graph structure. You don't need to assume a certain model of the graph and then say, yes, I can recover that model. This is stronger, right? And what does it say? It basically says that that the cluster S this procedure will find is provably near optimal. It's a quadratic factor away of this optimal cluster that is computationally intractable to find. That is kind of that we'll never be able to find in the real data, right? So that's the good thing. Why is this nice? This is nice because you are basically inheriting like 40+ years of research in spectral graph theory. You can literally implement it in about 10 lines of MATLAB. It's scalable. We were able to run this on the Twitter graph with 1.4 billion edges in a couple of hours. And why is it also cool is because it can be applied to directed, weighted, unweighted, signed networks. Let me comment now on a few of these things. So first, before people were asking about scalability, right? What is the expensive part of this operation is how they get from the original graph to this weighted matrix. And usually the motifs we are interested in are small. They have like 3, 4, maybe 5 nodes. So for those types of motifs, it's actually, in some sense, fast to count them. The counting procedures, the complexity, I think, is linear in the size of the network, but exponential in the size of the motif. So if the size of the motif is small, then you can run these things on big graphs, no problem. And once you have this matrix, which is sparser than the original thing, so you can always store this, then all you have to do is compute one eigenvector, which again is not too expensive. So that is one thing I wanted to say. The other thing I wanted to say is what is nice is that because you go here from this network, which is whatever it is, to this undirected graph, what you are essentially doing is here you could have edges of different types. You could have edges having weights, or edges having directions, or having signs attached to them. You don't really care because you can always apply spectral clustering to this matrix, which is now weighted, but symmetric, and everything is fine, right? So it allows you to define very funny motifs and still be able to create the weighted matrix and then cluster it. Okay? Let's see. I have 15 minutes left. So let me show you 2 applications of this. And I'll show you an application where we don't know what motif should be looking at, and I'll show you one where we know what the motif is. Right? So the first one is I don't know what I'm even looking for. Here's the question. Right? So what we will be looking at, we'll be looking at food webs. Food webs are networks that try to describe ecosystems. Right? The ecosystem we'll be looking at is some ecosystem in the Florida Bay, in the sea of the Florida Bay. So what are the nodes? The nodes are the species, are the organisms, and edges are what biologists call carbon exchange. And carbon exchange is which organism is eating which other organism, right? The cow and I are exchanging carbon, right? Because I eat steak, right? That's kind of the idea, okay? So they go and they measure these things, and they go in and they figure out who's preying on whom, okay? So this means that this particular organism is being fed on by that particular organism, right? Here, this thing is being eaten by that one, so the carbon goes that way. So here, different motifs capture different kind of energy flow patterns in this ecosystem, right? And the question is, how is this ecosystem organized? Which of these motifs, and there's 13 of them, allows me to extract the structure, and based on what motif is the structure of this ecosystem kind of organized, right? So the way we will do this is we will run our spectral clustering method separately for each of the 13 motifs, and we will examine these sweep profiles to see which motif allows us to kind of find interesting good clusters. So to show you what I mean by that, just for the 3 examples, this is my sweep curve. Here are the sets R. This is the conductance. Lower is better. And here are the conductance curve if I cluster the network based on different motifs. And what do you see is the following. You see if I'm using M8 or M5, I don't get good clusters, right? There's no kind of sharp drops. But if I use this motif M6, I quickly find good cuts in the network, okay? So it seems that motif M6 is a useful motif. So what this tells me is that to find clusters, M6 allows me to identify these clean, good-looking clusters, right? And M5 and M8, they don't reveal kind of good clusters, okay? So it seems that this food web is organized based on this particular pattern. And if you now look at what are the clusters you get, the clusters you get, I'm showing you here. So far, I was telling you only how do you find the best cluster. The way you can find multiple clusters is either compute more than one eigenvector of the Laplacian matrix and then do k-means clustering, or think of it that you take the entire network, take out the cluster, have the rest of the network, take out one more cluster and keep iterating. So the clusters that we identify here, I show you to them in colors. And it turns out that these clusters are correspond to what biologists call aquatic layers, and we are able to identify these aquatic layers much better than what previous methods were able to do. And to show you an example of how these aquatic layers look like, I think I'll show you a picture of this cluster and I'll show you a picture of that cluster. This is what I'm doing here. So this is this particular fishes cluster up here, and that will be the micronutrients, right? So what do you see in this cluster? You see that it is exactly this motif M6, but kind of rotated for 90 degrees to the left, right? You basically see the bidirectional edge here, and then you have this unidirectional edge. So you basically see this particular thing, kind of this template replicated here in this cluster many times. You see the same type of thing here. What do you see here is now, these are all the bidirectional edges, and then these are then the unidirectional edges here, right? So basically, it's the free bacteria is exchanging carbon with all these other things both ways, and then the bacteria and all these organisms either feed from whatever is being input to the ecosystem, and water POC is just kind of carbon that is freely flowing in the water. Another thing why this is interesting, why this motif makes a lot of sense, is because this is a marine ecosystem, right? So it's like, if I go to the way biologists draw this, right? You basically, this network operates in layers, right? You have this top layer where there's lots of light, and then you have kind of other layers in the ecosystem. And if you look at the motif M6, basically you have organisms in the same layer eating each other, and they also get food from the stuff above them, right? Kind of whatever comes from the top, they feed on that, and then they feed inside it, right? And that's why this makes sense. Okay, that's the first one. I want to show you just one more because this is interesting because you can apply it to signed networks. So here I'm applying this to gene regulatory networks, and the interesting thing is that regulation is a signed type of relationship. And biologists have said that feedforward loops are important to understand these types of motifs, these types of networks. And what do I mean by feedforward loops? Here are these feedforward loops, and these feedforward loops are what biologists would say coherent. Coherent in a sense that there is either 3 pluses or 2 minuses and a plus. So what I can do now is to say I'm interested in partitioning based on all these motifs. So when I create a weighted network, the weight of the edge will be number of instances of any of these motifs that edge participates in. Right? So here it has to be a feedforward loop, and the edge pattern has to be one of these 4 different. Sign pattern has to be one of these 4 different sign patterns. And if I now create the weighted matrix, I can again run spectral clustering, and again I can go and identify clusters. And here again, experimentally, the clusters have been verified and pre-labeled for us, and we can detect them much more accurately than what other methods would do that only kind of just look at the edges of the net. So with this, I can also show you the structure of the clusters defined, and you see these feedforward loops. For example, right, here's the feedforward loop and another one here, and so on. For one particular cluster, here is another cluster, genes kind of regulating drug resistance. You see kind of these feedforward loops, right, go this way. So it's interesting that basically based on the motif you cluster, and you look at the clusters, they have many instances of that motif you cluster. Okay? So this was I just quickly finish, right? So I want to maybe spend 2 slides on asking what are some interesting questions. It's interesting to take this idea and kind of push them further in terms of how do you think about doing these things in networks that are not static? How do you think about trying to identify different types of connectivity structure, right? So not just thinking about extracting bipartite subgraphs, maybe parts where, I don't know, there are cycles, things like that, right? Like, how do you model these overlaps? That was a good discussion before. I showed you that kind of they are denser, but the question now is how they are denser. Are they denser in every network? If they are not, how should we kind of faithfully model that? And then what also becomes very important is how do we assign some kind of robustness or significance to these clusters we extract, right? I have a method, it comes up with the clusters. How do I know how much to trust those clusters, right? Which clusters are significant, whatever that means, sorry. So that's one. And then in terms of the second part, what becomes interesting is how do you study larger motifs, right? What I presented works for 3, 4, maybe 5 nodes, but then it's very hard because the number of possible motifs explodes, and they are amazingly hard to count. So, you know, what do we do? The second thing I think that was elegant in the last part was that kind of all we really did is we came up with a kind of clever, this kind of technique that allows us to create a weighted matrix. So you could start thinking about how could I take a graph and create a weighted matrix out of it in some other clever, interesting way, right? What are other strategies to create weighted adjacency matrices? And you can also think about being able to analyze networks at this notion of higher order network structure, but not just at the level of motifs, but other types of higher order structure in terms of random walk or any kind of spreading processes and so on. So with this, I'm actually done. So happy to take questions.
Hi, thanks. Going back to the section where you had using node information, find these clusters. You've got some cool clusters about some of your students, a German student, German friends, and there's a cluster about Americans, PhDs, and stuff like that.
Yeah, yeah.
So yeah, in your summary, you were talking about we need ways to figure out how to trust these clusters. I just wanted to ask if you'd done any sort of cluster quality checks, and if you thought about things like point-wise mutual information, maybe do some sort of coherence measure on these clusters.
Oh yeah, yeah. I didn't have time to go into this. There is quite a lot of ideas how to do this, right? So, but the biggest problem in some sense is what is the ground truth, right? What are the ground truth clusters, right? And we have a kind of papers and that actually introduce this idea of ground truth and what could the sources of ground truth be. And once you have those sources, yes, then you can start measuring some kind of correspondence of what you detected with those ground truth things. And you can use mutual information. You can use some kind of matching ideas to match detected clusters with the true ones, and then measure some notion of correspondence. There are different ways to quantify this. What is usually hard is to come up with ground truth. So here we actually had a Kaggle competition where we worked with Kaggle first to collect data. We had a few thousand people go through all their, we created a Facebook app where people could go through all their 1,000 friends and label them, say, oh, I think, you know, you belong to this cluster, you belong to that cluster. And then we said, how do we uncover that? So that's what I'm showing here. And two of the people who participated there were my students who allow me to share the data and talk about it. But there were thousands of others. That's one way. Another way, another source of ground truth is, for example, to say, if I look at academic collaboration networks, you know, what communities do I expect to see is this kind of scientific communities. What are scientific communities defined by? They are defined by conferences. So, you know, let's say I identify clusters and then I say, how well do they correspond to publication venues, for example, right? That's a less reliable notion of ground truth. Or another place that you can take is, you can take an Amazon network of products and which products are co-purchased together. And then you can start asking, do these clusters correspond to product categories? And again, that's, you know, in some cases a good notion, in some cases not so good notion of ground. So it's a hard problem. Where also the notions of ground truth are easier to get is in biological networks, because you can think of these communities as predictions about what the modules are, and then, you know, a biology PhD student will spend a year in the lab trying to verify that what you identified is really true. So and what they do is many times they have some other ways to identify these modules. So there is kind of a ground truth set of those, and you can ask, can I identify them based on the network structure? So that's kind of the entire idea. Yes, at the back.
Thank you, very nice talk. Concerning sensitivity analysis, so the procedure that you use to count the motifs and then you use to create this weighted graph. Say, for example, if you have some noise in the observed edges in the graph, how robust are you with respect to this kind of stuff? Because in real life, you don't observe a graph, you observe a graph with some noises on the edges. And maybe so for example, if you observe a graph, and then you get some community structure using this stuff, and then you add some noise, some observation noise to the edges, maybe everything changes.
That's an excellent question. The question then becomes, I guess, what is your noise model? What we found is that I can show you one thing. I don't know if I have the slide. Maybe I have the slide. Let me find it. Yes. I'll give you an example. So one thing you can do with these methods that is cool is that you can also create what is called these local clustering methods, where the idea now is that you are given a graph, you are given a seed node, and you just like to find a cluster around the seed node. And why would you want to do that is because you can think of a network as being super huge, and you don't want to partition the entire network. You just want to find what cluster does this seed node belong to. Okay? That's kind of one thing I didn't talk about. But what I wanted to show you is this thing with regard to the noise. So what am I showing here is in graphs, if you make this simple assumption, let's say you have adjacency matrix and you have two clusters, and you have the probability, let's say alpha, that people connect with one another here inside the cluster, right? And you have this other probability mu for edges across clusters, right? Then let's say we fix alpha to be some value, and then let's say we are now increasing mu, right? When alpha equals mu, there is no clusters, right? It's just the same density. There's no way for you to detect that these guys are a cluster and those guys are a cluster because everything is equally well connected. Okay? Does it make sense? So now the question is, how well can you detect these two clusters as you are increasing the value of mu? Okay? When mu reaches alpha, there's nothing you can detect because this is just a uniform mess. Okay? So what I'm trying to show here is and parameterization of mu is not exactly as I drew it here because it doesn't go all the way to 1. But the point is the following. If you have an edge-based method or a triangle-based method, the question is how well here in terms of F1 score can you detect the clusters as you increase the density of these cross-cluster connections. Okay? And what do you see is that at some point in time it will just break. Right? So, and the interesting thing is that the edge-based method breaks sooner than the triangle-based method. So this is in the I agree. So exactly. So this is in a planted click model where you can actually see how kind of what's the difference in density between the cluster versus the background. And the thing is that actually there is like a fundamental resolution limit because these things are random events and there is some variance here. You can actually show that when alpha and mu become too similar, there will be no statistical difference in terms of connectivity inside the cluster versus across clusters, and you won't be able to detect those clusters. And you know that theoretical threshold is somewhere here, and the triangle-based method is able to get closer to that threshold than the edge-based one is. So what does this mean? It means that you can add lots of, in some sense, random noise, if you like. You can increase the number of cross-cluster connections. So basically, you can make the cluster kind of go more into the background, and the triangle-based methods will be able to still detect it better than the edge-based ones. So that's one way that I can talk about robustness to noise, right? Because here you can think I'm in some sense adding these cross-cluster edges, so this thing is kind of getting pushed into the background. It's kind of disappearing, and the question is how far can I detect it? This is now for two different null models. This is for the planted model, as Shai said, and this is for another model called the LFR model. It's kind of something similar but a bit different, and you kind of see this is kind of empirically in both. We see it works better, and there's some statistical, some theory analysis follow-up by Michael Mitzenmacher, who I think they were trying to prove these things rigorously. Of course, under this model. Good. Anything else? Yes. Maybe I don't know. I don't know. I'm not entirely sure what analog are you looking for. So let's talk offline. Yeah, I wouldn't. Anything else? Good. Then let's end here. Thank you very much. Have a good coffee break.